Hello viewers, welcome to another episode of Space Science with Python. Today we will dive deeper into the topic sky coordinates, and we will cover the ecliptic coordinate system in our today's session. So we will not compute the state vector or positional vector in XYZ coordinates, but really in sky coordinates, as I showed you in the previous videos with Stellarium. Now, I already prepared a small script. So here in the beginning, I'm importing some default libraries we need as always, like SpicyPy, like Pandas, Matplotlib, and so on. I already import some kernels, and I'm computing the date time for today's date. Today's the 13th of October, and I converted already into the ephemeris time. Now, what is the goal? The goal today is I would like to show you with Matplotlib and SpicyPy how we can plot, for example, the Sun, the Moon, Venus and Mars in our sky map. Of course, you can later add more planets like Jupiter, like Saturn, because currently you see them very bright in the night sky, which is also quite nice to observe. And today it's just about just a few planets. Later, or not in today's session, but also in the future sessions, we will also cover the equatorial system and also the horizontal system. Now, this is something for the future videos, but let's dive into the code now. You may ask yourself, if you're maybe an expert in the space science topics and you know some more libraries, why not using AstroPy? AstroPy does everything for me, so why should we bother with Spice and Matplotlib? Well, I would like to cover really the basics first to see how this works, right? I mean, AstroPy uses also some computations and libraries in the background, and here we are really on the very lowest level to create our figures, to create our data frames, our results, and so on. Now, we could start with our first cell. First, we would like to create a pandas data frame with the solar system, some solar system objects. Now, this data frame appears a little bit useless because we will not cover a lot of dates, only today's date, but well, we can still stick with the pandas data frame. So if you want to later extract this as a Excel sheet or so, feel free to do it. So first we add our ephemeris time, of course. This has been computed here. And then we add also the UTC timestamp in a second column in a human readable format. And we can do it here. Yeah, so this should work. And now let's create also a dictionary with the objects of interest. So in our case, we create a dictionary, and this dictionary contains the Sun with the NIF ID 10. We add Venus with the number 299 and our Moon with the ID 301, and of course Mars. Now for Mars, I just checked the kernels. I think, if I recall this correctly, with the kernels we are currently loading, we can only use the ID 4, so not 499. I think, I mean, here it's maybe just only a deviation of a few kilometers or so, but this somehow caused an error during the testing. Now PD is not defined yet because I didn't run the first cell, so let's go through it. Let's check our data frame quickly. And there with the ephemeris and the UTC timestamp. Okay, nice. Now we can add our bodies into the data frame. So what we would like to do, we would like to add the longitude and the latitude coordinates, the longitude and latitude values of the ecliptical coordinate system. And for this, we are creating now a simple for loop where we just iterate through this dictionary and compute the positions. So we compute first the state vector, And based on the state vector, we can then compute the projected coordinates on the ecliptical coordinate system. So how do we do this? We are creating a for loop through the dictionary. So let's say we create some body name, and then we say, okay, we would like to add a position vector or something like a direction, like direction of a certain object, like our body, like the direction of the sun, with respect to the Earth, or the Earth is like the observer, the center, and then let's say ECL, like ecliptic coordinates. Now this will probably be a very long line, so let's make a new line here, a break. What do we need to compute the positions? You may already know from the last sessions, we need of course the ephemeris time, and we need to apply a function along all ephemeris values. In this case it's only one, so this may appear a little bit like an overkill, but if you would like to compute it for more, you already have the code snippets here, and you can just add it or see how, for example, the sun or the moon is creating a path on the night sky. So feel free to change the code accordingly. Now we compute the simple positions. First, it's of course the target. The first target is, in our iteration, it's the sun. So we have to say the body name. So it will give us the number 10 as the target. Body name, new line. And then we have the ephemeris time, which is of course coming from the apply function. Our reference frame, we already had this, I think, in the very first or second video, the Ecliptic J2000. Remember also the correction. We can add now correction for the light time. And then at the end of the day, the observer, and in our case, the observer is 399, it's us. And since we only want the function returns not only the state vector, but also the light time. So in a two-dimensional vector, or list, we only need the very first one, the x, y, z coordinates, and that's basically it. So let's make a quick check how this looks like. And there we see the direction of the sun with respect to the Earth, Venus, Moon, and Mars. We can later verify this also with Stellarium to see whether it makes sense what we are doing. Now we have the XYZ coordinates. Now we want to compute the longitude, the ecliptical longitude and ecliptical latitude values. Now we could now simply, also here we can just create again a lambda function where we apply a computation on the vectors. And for this we say, okay, something like the sun or moon, so the body name, longitude, red eclipse. So the values will be returned in radians, not in degrees, and we need also radians for Matplotlib. Of course, it's like not very intuitive like degrees for a human user, let's say. But we just want to plot it today. So if you want to later also convert it, you can also apply the numpy degrees or math degrees function on the radians results. Okay, so how does it look like? We will apply a function on our computed vectors. We computed them here. And maybe I should also move this to a new line first. Now, if you may ask yourself, well, why I'm creating here a new line and not there, or just adding it later. There are rules how to make this line break. So there are a lot of tools that can be embedded, for example, into a CI pipeline if you're creating Python scripts, so really .py files. You have then scripts like, or libraries like Pylint, you have libraries like Black, for example, that really reformat your code according to the PEP standards. But here in Jupyter Notebook, it's, well, yeah, you just follow some kind of rule, add comments also, because a Jupyter Notebook, well, sometimes leads to a little bit chaos. So you have to be really careful not to make it too chaotic for a reader. So we are now back here. We apply a function to the vector. And what is this function? Well, we use SpicyPy and we use a new function called regrad. So it's converting rectangular values, so like three-dimensional vectors, into coordinates like longitude and latitude values. And the longitude latitude values, of course, depend on the reference frame you defined before, like here the Ecliptic J2000. If you have another coordinate system, of course, the regrad function returns other results accordingly. Now, we have like three values. So we can check here the SpicyPy documentation tells us that it returns three values. The very first is the distance between the observer and the object. So it's like the Euclidean distance. So this would be the 0 entry. The first one is the longitude value, and the third one is the latitude value. So basically we don't need the distance, we just need the longitude. In our case, it's simply number 1. Of course, you could put everything to one function, but let's keep it a little bit, let's keep our overview, let's say. And here we have the latitude, and there we have number 2. So this is how we then compute the longitude and latitude values in radians. Now you can really again apply NumPy degrees or math degrees to convert it into degrees, but again in Matplotlib we need the radians values to visualize our data. Now, how can we visualize these data? First, let's have a look. Now this is simply some radians values, as you can see here. Oh, I would like to, well, I somehow cannot scroll to the right. That's kind of bad, but that's not a problem. Let's maybe just simply show the longitude values of, for example, the sun. Of course, I should have run it through first. Yeah, there we are. There we have the longitude in radians. Good. Now let's have a look first in Matplotlib how we can plot things in on some projections. And in Matplotlib, they're not talking about astronomical projections also, they talk about geographic projections. So they assume that you are working on some map data, and they have a different projections. For example, the Eithov projection, Hammer, Lambert, or the Moll-White projection. Now you see that the longitude and latitude lines, they have different shapes. Some up here, they are parallel. Here, everything is curved. And all these projections have their advantage and disadvantage. And I don't want to dive too much into detail. For example, here the Eithov projection is length preserving along the meridian, the central meridian, and also along the equator. And since we are computing everything in ecliptical coordinates and our ecliptic will be here, or will be the equator, let's say, we can stick with the Eithov projection. So let's have a look first how this looks like. So we create an empty file, an empty graph first to get used to this kind of projection stuff. So dark background. Of course, the night sky is dark, so we need it as always. We can now create a figure with the figure size. Now, somehow I'm a little bit struggling today. Figure size 10. And then we can create a subplot. And in the subplot, we say that the projection should be ITOF. And then we can also add a grid. It's quite important to orientate. Otherwise, it would be a little bit difficult to understand. And then we can also, of course, create some longitude values and latitude. Let's say it in degrees. Latitude in degrees. And there we see it. So although Matplotlib expects us later to add radians values, we Matplotlib plots them as degree values. So this is basically it. We can then also make a save figure. I think I will add some figures in the GitHub repository. So this is how it looks like. And now we have to continue or add our values into this graph, and let's see whether this will work out of the box or not. So let's go with a new cell, and you already may see why. Okay, the latitude values here, it makes quite sense from minus 90 degrees to plus 90. But here it's like the definition of geographic coordinates. We have here to the east increasing numbers, 30 degrees, 60, 90, 120, and to the other side with minus 30, minus 60, and so on. But if you recall Stellarium, then, or also about the last session, the longitude values for sky maps are defined from 0 to 360 degrees, or from 0 hours to 24 hours in equatorial coordinates. So how should we deal with that? Well, I would say, yeah, let's do some plotting and try to figure out how this may work. Now, first, let's make some copy-paste of what we already did here. So I just leave it here empty. Then we can, for example, add first a small title. So for example, if you would like to compute the position of the moon and the planets, then it's of course quite important or nice to have the UTC timestamp as a title. So it changes of course every day, right? So, or every minute. So it would be important to get this info first on as a title. So the font size should be like 10 or 12. Let's stick with 10. Yeah, so we have here the UTC. 10 is also the perfect size. I think 12 would be a little bit too large. We need also to add some colors maybe also. So I should have done this in the dictionary, but we can create a simple array here and just preserve the order of the objects. So we had the Sun, Venus, Moon, and Mars. Okay, let's give the Sun the value, the color yellow. Yeah, let's give Venus orange. Oh, it's also quite, yeah. So it's very cloudy planet, so yeah, maybe orange would fit, I don't know. And then we have our moon. I would say gray would fit perfectly. And then we have, of course, Mars, and there we have the color red. I think this fits quite perfectly. And now we can iterate through the body names and the body colors. So again, next time I should have done this into one single dictionary where we just iterate through the dictionary and of course the body color array. And now we can plot it. Plot, where we see or say, okay, the same logic can be copied from here, the longitude and the latitude values. So let's take this one first. Yeah, I copied it correctly. This is like the longitude values, or let's say the x values. Then we have the y values, the latitude values. So we have to correct this one here as well. And then let's add some parameters for the plotting to have it more fancier, like the color, the body color. It's defined in the for loop on the top. Then, of course, a marker. So I would say round would be quite intuitive. The line style can be set to none. Marker size. I just checked before. 12 was quite good if I recall this correctly. And of course, label. I don't know if this is needed. Should we put in label? Yeah, maybe for legend this would be helpful. I mean, the colors don't always speak for themselves. And then maybe capitalize, because otherwise everything is formatted weirdly. So like this. And then, yeah, maybe we can add also the legend already. So some formatting. The X label is then the ecliptic longitude in degrees. The Y values are the ecliptic latitude in degrees, Y. And we would also like to add a legend. And of course a grid as well. Did I copy it? I already copied it here. Good. And then we could also theoretically save the figure afterwards. So let's plot it. And we have an error in the zip. They are already dictionaries and arrays. I don't need this one. Yeah. And what do we see here? Well, we only see the moon and the other objects vanished. Okay, what happened? Did we do something wrongly? Now, this is something I wanted to show you, that we have to do some data engineering, let's say, for our plotting routine, because as I said, maybe you remember the value of the sun. It was something like 3.7 or so, right? So a little bit more than pi. And Matplotlib, the geographic projection or the coordinate system, is defined at 0 in the center, and it goes to 180, and then it goes back to minus 180, increasing to 0. So any values larger than half a pi are gone. They are just vanished. And the same thing applies probably also for Venus, Mars, yeah, and the sun itself. Only not for the moon. So we have to somehow think how we should change this. And maybe to get a better feeling, let's change the tick values here. So what do we expect here first before we dive into the conversion? So the X ticks needs to be converted. We have we need the radians of values from minus 150 degrees to 150 degrees. So first of all, the ticks, they start in Matplotlib from minus 150, go to 150 in 30-degree steps. Now here this NP arrange creates a list with values that go into 30 unit distances. So 100 minus 150, minus 120, minus 90, minus 60, and so on. But it goes up to 150. So 180 is not considered anymore. So this is now the values we would like to replace. And with what would we like to replace them? No, thank you, auto correction or fill up. This is not completion. This is not what I want. Okay, first, this bracket is wrong here. Let's check. Yeah, it doesn't. It looks right. We want to replace them with new labels. And what are these labels? Of course, now I could also do some kind of a for loop, but let's do it step by step. So the first entry here on the very left side, or let's say in the center, we would like to have 0 degrees, then 30, then no, so minus, no, not minus, but 330 and 300 degrees, 270, and so on. So the point is that our coordinate system in the night sky goes from the center to the left. So if we just go back into Stellarium, let's open it, should have done this earlier. We can take a look. Now this takes a moment, and also the loading takes always, so the menus here on the left and the right. Here's the sun currently, the moon. So the moon was plotted, right? But the sun somehow vanished. And I think now everything loads. Yeah, perfect. Let's turn off the everything and let's create the equatorial grid. So the equatorial grid, as you can see here, there is 0 degrees and it goes on the left-hand side. So to the left, we have now plus 15 degrees, plus 30, plus 45, plus 60, plus 75, and so on. And then on the right side, we have plus 345, 330, and so on. So the geographic projection goes from the center to the right in Matplotlib, but here we have to invert it even. So we have to be very careful. Let's go back to VS Code and think that here we would like to have 0 degrees, 30 degrees, 60, 90, here 150. There we have then, here's 180 degrees, so here is 210 and so on. So we can now have to think a little bit. 120 degrees, then we have 90 degrees, 60 degrees, 30. I know you can do this in the for loop, just wanted to explain it step by step. Now this part here is the part here on the left side. So we go from 150 degrees, 120, 90, 60, 30 to 0. And now, maybe let's make a line break. We have the right-hand side, and the right-hand side is then 330 degrees, 300 degrees, 300 degrees, 270 degrees, 240, 210 degrees. And again, 180 degrees is here, this corner. So this the point that goes from the left side to the right side and vice versa. So let's plot this again. Okay, we adjusted our coordinate system a little bit, and now we have to think a little bit how we have to, what we have to do with our data. Now I would suggest that it go in the for loop, so body name in Solstice dictionary, and there we maybe add a new column. I would suggest a column that is only for plotting, because if we want to later continue working with our data, we need the values for some further coordinate transformations. We need the actual values and not the ones that are needed for plotting. So this is like only an adjustment for Matplotlib. Now the latitude values, we don't need to change them really. We only need to change the longitude values. So we say now longitude radians for plot eclipse, let's say. And this is equal to here where we have to convert now the longitude values. So we already defined it here, I guess. Yeah, this one. We have to convert the longitude values into certain logic. And before I start working here, I should also create here RUT for plot. So otherwise we forget it and then I'm just stuck. And then we need to apply a certain logic. Now, how does the logic look like? Well, first of all, we have to invert our coordinates, right? So originally it goes in Matplotlib from the center to the right. Here it goes from the center to the left. So we have to multiply -1 to all our results. -1 times x. But we have also values that are larger than 180 degrees. So what do we have to do? We have to, so let's take an example. We have 200 degrees. And if we have 200 degrees, it has to switch the sides, of course. And what can we do? Well, let's take the logic. Okay, 0 degrees is in the center. It goes to the, now we take the geographic projection first. So it's a little bit confusing, but please try to follow me. From the center to the right is 180 degrees. So we have here, let's say, something which has 200 degrees. And 200 degrees would correspond, or let's make it more easier, 210 degrees would correspond to minus 150 degrees. So what do we need to do? Well, what we could do, for example, is we could say, okay, we take the modulo of 210 degrees with respect to 180 degrees. So modulo means that from the 210, 180 degrees are removed. So we have a remaining value of 30 degrees. So then our point would be here at 30 degrees. But we want it at minus 150 degrees, which means that from this result, we have to subtract again 180 degrees. So we have to make the modulo of 180 degrees, then it moves here, minus 180 degrees, and then our dot should be here, which would be what we expect. I know we have now here different ticks, but the ticks do not have any effect in the computation logic, only in the logic or only in the visualization, not in the computation logic. So we have to be very careful now. So what we need is we have to, again, modulo 180 degrees minus 180 degrees, and this in radians. So 180 degrees is pi. Now let's check. This is x, but this is our inversion logic. First, we have to say, okay, our result or our value, like 210, we must apply a modulo like numpy.pi. Of course, I could also already extract this, right? But could also simply extract 360 degrees, but let's stay it like this. And then we have to subtract minus pi. So let's make it more clearer with brackets here. So this is the logic, like 210 degrees would be then here the result, the remaining value would be 30. 30 minus 180 would be 150. And we have, of course, to invert it. Now, now this logic does not need to be applied for all values, only if the x value is larger than 180 degrees. Otherwise, we can simply say, yeah, okay, just invert it. So let's make some thing here. Now I can stick it like this. Okay, now let's run this cell and rerun this cell again. And voila, we see our results: the Sun, Venus, Mars, and the Moon. Now, do these results make sense? Of course, I would like to verify this now. We can now use NASA Horizons. I explained it in one of the videos, or we could also use now Stellarium, which we could take as a, let's say, ground truth. And of course, we cannot use Stellarium all the time. So later, if we are inside the Saturn system, computing some coordinates to the moons and so on, we cannot use Stellarium because Stellarium doesn't allow us to do, let's say, more complex computations. But here we can just first see whether our logic makes sense or not. So let's see, the Sun is at around 200, or let's say Mars is at around 210 degrees longitude. Now the planets and the Moon are almost very close to the ecliptic plane. The Moon is at around close to 150, and Venus between 240 and 270. Now let's have a look. So first the Mars. So this is Stellarium again working. Where is Mars? There is Mars, and you can see Mars is on this particular line, and we have it here at 210. This is strange. Let's move back. Yeah, 210, not 270. Yep. So this makes sense. I just confused myself. The Mars is almost perfectly on the 210-degree line, and this fits perfectly. Venus was between 240 and close to 270. We have Venus here, and it's below the ecliptic. Here's the ecliptic. So let's take a look back into, and let's rearrange the windows a little bit. Yeah, it's also makes sense. Now, of course, we have to compare the actual values. It's just about, just verifying visually with the eye. And then we have also the moon. Let's check out the moon around above the ecliptic and close to 150. So probably something like, I don't know, 140, 145 or so. So let's move to the left. There's Jupiter and Saturn. Take this as an exercise to do it with them. And there is the moon, and it's also very close to 150. So yeah, 145. So yeah, very close here. This makes also sense. And it's above the ecliptic plane. Yeah, here's the ecliptic plane, 0 degrees. So this makes sense. Now, wow, we just created our very first sky map plot in ecliptical coordinates with the Sun, Venus, Moon, and Mars. Now, as a summary, of course, it was quite complicated, I have to admit. Especially the logic of converting the ecliptical coordinates as they really actually are returned by SpicyPy, converting this into a logic that can be used for Matplotlib, especially this part here. This is really confusing, I have to admit. And of course, there are other libraries that are especially designed for astronomical purposes, like for example, AstroPy. But I wanted to really dive here into this with you and show you the logic behind it. I hope you learned something. This is the ecliptic coordinate system. Everything is as expected. And next time we will dive into the equatorial coordinate system. So the one that is the, let's say, Earth-centric coordinate system with the ecliptic north poles, where we have our track our stars with a telescope mounting and so on. So this will be done next time, where we have a little bit more time, or we don't have to be bothered again with the logic of Matplotlib because we already created the scripts here. We will just convert everything from ecliptic coordinates to equatorial coordinates, and we will learn another SPICE function that will help us to do this. I hope you enjoyed the video. If you have any questions, reach out to me via a comment or DM or on Twitter. The links of today's session are again in the description, and I hope you will find some fun or have some fun with coordinate systems and with the more complex visualization methods we are starting today now from now on. Yeah, take care, goodbye, see you next time.